Here's a rather simple differential equation. Our idea for solution here, to solve this differential equation, we integrate on both sides to find y to be 2x. Now, another perhaps more conceptual idea of this is to say that we're looking for the function whose derivative is 2. That's just a more of a general way of looking at this situation. We can actually check this then by taking the solution that we found and finding y prime to be 2. And that's what we started with up here. Now there's another idea though involving solution, and sometimes we have to take an approach to the solution of a differential equation that's more akin to the solution to equations in general. You know, solutions to linear, quadratic equations, those kinds of equations are replacements for the variables that cause the equation to become true. So if we're thinking, for example, that we want to find out if this is a solution of this differential equation, then we need a y double prime and a y and plug into this equation to see if it makes it true. You see, and then we have a solution. Well, oh, by the way, this is called a second order differential equation because we have a second order derivative involved here. We'll have a little more to say about order and such things at a later time. All right, but at any rate, if we want to evaluate whether this is a solution to that, then what we would do is take this and find the second derivative. Well, let's see. Y prime is 4e to the negative x times the derivative of the negative x, which is negative 1. So it's negative 4e to the negative x. Y double prime means the derivative of this is this times the derivative of the negative x, which is negative 1. So we get 4e to the negative x. Now, to evaluate whether or not this is a solution to that, then from this we got y double prime. We have it right down here. So we take this, put it over here, and replace y double prime with what we calculated down there, 4e to the negative x. We take our y and plug it in here and see if we have truth. Well, we do indeed have truth, so yes, that is a solution to this differential equation. Now, solutions to differential equations can be thought of as being either general or particular. A general solution would look something like this, and a particular solution would look something like this. Now, particular solutions a lot of times emerge when we are given some additional information, usually at the front end of a problem, and we're able to identify the value of a constant. Let's look at how we might view this idea of determining whether or not we have a solution. Now, notice that our flow here in this section so far is that we're not really solving the differential equation. We are trying to tell whether we have a solution or not. It's quite a bit of a different point of view from where we have been before. But we need to be able to do this. There are certain situations where it just isn't trivial for us to solve the differential equation, but it's very important whether or not we do indeed have a solution. Okay, here's a problem where it says, is this a solution of that? Now, notice that the differential equation is in the form y prime equals some expression. And when our differential equation is in this form, usually our method of determining whether or not we have a solution is to take our candidate as a solution and just find the derivative of it and see if we can put the derivative of that into this form, you see. So that's what we'll do. We'll take this, and implicitly this becomes the derivative. The implicit derivation is 2x, then 2y prime, and then c times y prime. And now we'll manipulate this a little bit and see if we can put it into this form. Well, let's see. We've got a y prime factor here and a y prime factor here. If I subtract the cy prime on both sides and then subtract 2x on both sides, we'll get this. Now I'm going to snag out the y prime from both of these terms. We get this, and then we'll divide on both sides by that binomial and get this. Now we're comparing this y prime with that y prime. Do they look alike? No. So we have to go through additional manipulation. Maybe we can continue the manipulation and make it look like that. It'll turn out that we can. But our first idea might be to notice that in this form we have a y factor in the numerator. Here we're missing a y factor. So let's just pop a y factor in there by multiplying by y over y. So in the numerator we'd have negative 2xy, and in the denominator 2y squared minus cy. Well, now what else can we do to manipulate this thing? Gee whiz, this doesn't have a cy in it at all. Oh, look up here. We have cy equals this expression. So let's take the cy that appears down here and replace with x squared plus y. So we'll have 2y squared minus x squared plus y squared. All right, so up here, that's what I've done. So minus x squared plus y squared, and then it clears out pretty quickly here. We have 2y squared minus x squared minus y squared. 2y squared minus y squared is just y squared. So in the denominator, negative x squared plus y squared, we have a sign change situation, so we can think of it as multiply by negative 1 over negative 1, if you'd like to think of it like that. Factor out negative 1 in both numerator and denominator. You can think of it like that and cancel. But at any rate, we manipulate it back into the form that we need to show that we do indeed have a solution to the differential equation. Let's answer this question. Is y equals x squared e to the x a solution of this differential equation? Now this equation is not in the form of the previous problem. We're going to have to make some fancy substitution here to be able to tell. We approach the problem like this. This is our candidate for a solution. So we take this candidate for a solution and we find its derivative. We find y prime. Y prime now is found by using the product rule, all right, on these two. It's x squared times the derivative of this plus e to the x times the derivative of that. So we have this. All right. So since this is y prime, we'll make substitutions into this differential equation. So we'll replace y prime with all of this. So we have x times the y prime, and then minus 2 times y. Well, the y is this, the x squared e to the x power. And then we just bring down the x cubed e to the x. And we just want to see if we have truth here, and it turns out that we do, and things drop out rather nicely on this particular problem. But at any rate, it's just kind of a double substitution situation and an evaluation process. This is negative 2 times all of this, which gives that, and x times these two terms adds an exponent on the x's here. This 2x squared e to the x minus 2x squared e to the x, they go out, and so we have x cubed e to the x equals x cubed e to the x. So we have truth, and therefore, yes, we do have a solution. Here's a problem in which we want to find a particular solution. It says for this differential equation, this is a solution. Find the particular solution given the initial condition that y equals 2 when x equals negative 3. The particular solution. Now, this kind of problem where we have a general solution here and we're looking for a particular solution sometimes lends itself to an interpretation graphically. You see, we can look at the graph of this equation as c takes on different values. For example, here's a look at the graph as c takes on values 1/2 and 1 and 2 and 5. Now notice that the graph is continually increasing, and so for all of these functions. Now let's look at what happens when c takes on values that are negative. Notice that for these values, for the negative values of c, the graph continues to fall left to right. Okay. So we would like that particular value of c that will give rise to a point on the graph of y equals 2 when x is negative 3. Algebraically, we can find the position like this. We take our general solution and we make it particular by putting in this initial condition. So let's see, y is 2 when x is negative 3. Replace y with 2 and x with negative 3. and find c to be 2 over negative 27, or negative 2/27. And so our form here, our y equals cx cubed, which is this form right here, becomes this. And we can write it in either of these two ways, but when we pop this into the computer and look at the graph, we can easily trace over and verify that the point negative 3, 2 lies on that graph.